It's been 4 decades of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system.
In the vast silence beyond our solar system, something extraordinary is happening, something no one fully understands. A 1970S spacecraft running on ancient tech is detecting forces, structures, and signals that defy the laws of physics as we know them. What did Voyager 2 just stumble into, and why are scientists saying it might rewrite everything we thought we knew about the universe? More than 12 billion miles from Earth, something extraordinary has happened. A spacecraft launched over 4 decades ago has crossed a boundary long considered the outermost edge of our solar system. NASA has confirmed that Voyager 2, a probe launched in 1977, has officially exited the heliosphere, the vast protective bubble created by the sun's solar wind. This makes Voyager 2 only the second human-made object in history to leave the solar system, following its twin, Voyager 1, which achieved the milestone in 2012.
Now, this is quite a story from NASA because for the second time in history, a man-made object has left our solar system. NASA is saying the Voyager 2 probe is now in a space between the stars after exiting the sun's protective bubble, which is called the heliosphere.
The significance of this event stretches far beyond a milestone in space travel. It's not just a matter of distance or endurance, though both are remarkable. What makes Voyager 2's exit from the heliosphere so important is the nature of the data it has sent back. As the spacecraft crossed the heliopause, the boundary that separates our solar system from interstellar space, it began to relay readings that challenged much of what scientists thought they understood about the space environment beyond the sun's reach. The heliosphere itself is a vast bubble of charged particles and magnetic fields that the sun emits as part of its solar wind. This wind creates a kind of shield that helps protect the planets from high-energy particles that fill interstellar space. The outer boundary of the heliosphere, known as the heliopause, marks the point where the sun's influence ends and the interstellar medium begins. Voyager 2's journey through this frontier revealed a space environment far more complex than previously imagined. Traveling through this region, the probe detected changes in the density of plasma, a hot, ionized gas that exists throughout space, and shifts in magnetic field patterns. These findings weren't just unexpected, they were fundamentally different from what existing models had predicted. The data seemed to show a space environment that was structured, active, and dynamic, not the quiet void many had assumed. Among the most surprising observations was the behavior of magnetic fields at the edge of the solar system. Before the crossing, scientists had predicted that the magnetic field would become more diffuse and weaker as the spacecraft moved into interstellar space. Instead, Voyager 2 detected a stronger and more organized magnetic field. This went directly against decades of assumptions, including what had been observed by Voyager 1, which saw a different field direction and lower intensity when it crossed the boundary years earlier. This went exactly contrary to all the boundaries years earlier. At first, researchers questioned whether the data could be trusted. After all, Voyager 2 is an aging spacecraft built with technology from the 1970S and running on a radioisotope thermoelectric generator that's been slowly losing power over time. Its instruments, while robust, were never designed to operate for this long or under such extreme conditions. Yet after multiple checks and verifications, NASA scientists concluded that the instruments were functioning properly. What Voyager 2 was detecting was real and entirely unexpected. Further analysis revealed that the probe had passed through a region where the properties of space did not match the solar wind or the known interstellar medium. Instead, the plasma was denser and colder than anticipated. This wasn't a gradual transition, it was abrupt. It seemed to suggest the existence of a transitional zone, something like a buffer between the sun's influence and the true interstellar environment. This region appeared to contain properties that did not conform to any existing definition of solar or interstellar plasma. The data suggested a liminal state of matter, something between the hot charged particles of the solar wind and the cooler, more stable conditions of deep interstellar space. This discovery alone was enough to prompt serious reevaluation of the heliosphere's structure. But it wasn't just the plasma that defied expectations. Voyager 2's instruments began to pick up variations in cosmic ray intensity. Cosmic rays, high-energy particles originating from outside our solar system, were expected to become more consistent and evenly distributed in interstellar space. Instead, the readings showed unpredictable surges, appearing in waves that pulsed and faded irregularly. There were even directional shifts where more particles seemed to arrive from one particular region of space than from others. This suggested some form of external force was guiding or influencing their path. Another layer of mystery came from the behavior of the magnetic field. Rather than dispersing in the way most models had predicted, it became more compressed and aligned in a consistent direction. Voyager 2's magnetometer recorded a sudden increase in magnetic field strength, almost 3 times stronger than what Voyager 1 had detected during its own crossing. This raised questions about whether the 2 probes had encountered fundamentally different regions of space, even though they left the heliosphere only a few years and a few billion miles apart. It was a reminder that even in the vastness of space, small differences in location can mean big differences in conditions. One of the most compelling aspects of Voyager 2's findings is that these results weren't anticipated. The models that scientists had relied on for decades failed to predict what the spacecraft encountered. And because Voyager 2 carries instruments designed specifically to measure magnetic fields, plasma, and energetic particles, it provided the clearest look yet at what lies beyond the sun's reach. The readings are still being analyzed, but their implications are already being felt across multiple disciplines, from astrophysics to planetary science. They suggest that the transition from the solar environment to the interstellar medium is far more abrupt, more layered, and more active than previously believed. The traditional view of the heliopause as a kind of fading line is being replaced by the concept of a dynamic, possibly shifting boundary zone, one that reacts not only to the sun, but also to forces in the broader galactic environment. This moment in space history isn't just about where Voyager 2 has gone, it's about what it has found and what it means for how we understand our place in the galaxy. The data coming from the spacecraft is prompting researchers to rethink some of the most basic assumptions about how our solar system interacts with the rest of the universe. The probe's instruments began detecting inconsistencies almost immediately after it left the heliosphere. One of the most puzzling was the behavior of plasma, the soup of charged particles that makes up much of the matter in the universe. Plasma from the sun, known as the solar wind, was expected to thin out and give way to interstellar plasma, which should have been cooler and less dense. Instead, Voyager 2 entered a region where the plasma was unexpectedly dense and cooler than what any existing models had suggested. This denser plasma wasn't behaving like anything scientists had previously measured. It didn't match the characteristics of solar wind, nor did it resemble the expected properties of interstellar plasma. It was, in essence, something entirely new. The spacecraft seemed to be moving through a transitional state of matter, what some researchers have described as a kind of interstellar buffer zone. This layer, invisible to telescopes and unaccounted for in theoretical predictions, appears to sit between the solar wind and the deeper interstellar medium. Its discovery suggests that the edge of our solar system might not be a sharp line, but a zone of transformation, where materials from 2 different environments interact in unexpected ways. As if that weren't enough, Voyager 2's instruments picked up strange patterns in cosmic rays, high-energy particles that traveled through space, many of them originating from far outside the Milky Way. In theory, cosmic rays should become more evenly distributed after leaving the sun's influence. Instead, Voyager 2 found that these rays were arriving in uneven waves. Their intensity would surge and recede, often in irregular and hard to predict intervals. Even more surprising, the rays appeared to show a directional bias, with more particles arriving from certain regions than others. This asymmetry suggested something else at play, possibly a large-scale magnetic structure or an unknown force field in interstellar space shaping the paths of these particles. If true, it means that our solar system might not be floating freely through a featureless void, but instead moving through invisible structures that affect how energy and matter behave on the edges of our celestial neighborhood. The magnetic field itself presented another major surprise. Rather than weakening, the field grew stronger and more aligned as Voyager 2 crossed the boundary. This was completely at odds with what scientists had predicted. The jump in magnetic field strength was significant, almost 3 times stronger than what Voyager 1 had recorded during its own crossing. Additionally, the orientation of the magnetic field was different, suggesting that the two probes, despite being relatively close in astronomical terms, had exited the heliosphere into very different kinds of space. Initially, some suspected that this could be an error in the spacecraft's sensors. After all, Voyager 2 is a product of 1970s engineering and has been operating for over 45 years. But repeated testing and signal analysis confirmed that the instruments were functioning as intended. The data was real, and it described a region that defied current understanding of helophysics. Among the more mysterious observations were interactions that seemed to show high-energy particles curving around the spacecraft, as if bending in response to some unseen force or structure. These anomalies were consistent and sustained, not random or isolated. This pointed to the possibility of organized patterns in interstellar space, something far more structured than previously believed. The notion that the space beyond the heliopause could contain coherent systems of fields and forces implies that interstellar space might be more like an ocean with currents, layers, and turbulence, rather than a still, empty void. Even more intriguingly, Voyager 2 detected changes in how radio waves traveled through this space. Signals sent back to Earth began showing subtle distortions. These weren't simple interference patterns. They included frequency shifts and modulations that hinted at complex interactions with the plasma environment. Some scientists believe this could indicate the presence of eddies or folds in the structure of space itself, patterns in the density or magnetic alignment of the material that surrounds our solar system. Such structures had never been considered part of the boundary zone around the sun, yet they now appear to be an essential feature of it. The idea that radio waves could be altered by small-scale structures within interstellar plasma has significant implications, not only for understanding Voyager 2's journey, but also for how we study distant cosmic sources from Earth. Another key discovery came from Voyager 2's detection of magnetic reconnection events. These are moments when magnetic field lines snap and realign, releasing bursts of energy. Such events are usually seen near stars or highly active regions like black holes, where strong magnetic fields and intense energy sources create the conditions for such reactions. The fact that similar phenomena were detected in what was expected to be a calm region of space came as a shock. The readings suggested rapid and significant shifts in magnetic polarity, sudden flips that produce short-lived but powerful emissions of energy. This indicates that the edge of our solar system might not be as passive as previously thought. Instead, it could be a zone of electromagnetic activity, shaped not only by the sun but also by the larger galactic environment. These events challenge the assumption that the heliopause is merely a passive boundary. Instead, it may act as a kind of energy interface, a place where solar and galactic forces meet, interact, and sometimes even clash. That makes it one of the most active and complex regions that a spacecraft has ever studied directly. Taken together, the data from Voyager 2 presents a picture of interstellar space that is anything but empty. It appears to be filled with structured magnetic fields, directional particle flows, variable plasma states, and even turbulence. All of this suggests that our solar system doesn't just float in space. It participates in a wider network of forces and structures that stretch across the galaxy. This level of complexity is forcing scientists to revisit the models they've used for decades. Many of the simulations that helped us understand the sun's boundaries relied on symmetrical, simplified assumptions. Voyager 2's findings show that reality is far messier. The heliopause is not a clean spherical shell around the solar system. It may be jagged, uneven, and shaped by both internal and external pressures. Perhaps most importantly, the discoveries raise questions about how the solar system interacts with the rest of the galaxy. If structures exist just beyond the heliopause that can alter the flow of cosmic rays, shape magnetic fields, and redirect particles, then Earth's environment is not just shaped by the sun. It is influenced, possibly in significant ways, by what lies beyond. Voyager 2 didn't set out to answer these questions. It was launched in 1977 to study the outer planets. That it's still returning groundbreaking data nearly 50 years later is a testament to its design and to the persistence of scientific curiosity. The discoveries it's making now are among the most profound in modern space science, not because they provide clear answers, but because they open new avenues of inquiry into physics, astronomy, and the very structure of space itself. One of the more intriguing theories now gaining traction is that the boundary region between the solar system and interstellar space may act as a kind of filter or shield. It appears to modulate the amount and type of cosmic radiation that enters the inner solar system. This wasn't entirely unexpected, but what surprised scientists is how variable and structured that shielding might be. The heliopause, once thought of as a relatively static shell, now seems to be a flexible and possibly fluctuating zone that changes depending on the galactic environment surrounding it. As the solar system moves through different regions of the Milky Way, passing through clouds of gas, pockets of magnetic turbulence, and possibly even dark matter concentrations, the shape and behavior of this outer boundary could shift. When the shielding effect is stronger, fewer high-energy particles make it into the solar system, but when the heliopause is compressed or disturbed, it may allow more radiation to penetrate inward. This could have significant consequences for Earth and other planets. Increased cosmic radiation can influence a planet's atmosphere, magnetic field, and climate. On Earth, for example, some researchers believe that past increases in cosmic ray exposure may be linked to changes in cloud formation or temperature trends. Others suggest a possible connection to mass extinction events, where spikes in radiation could have damaged biological systems or disrupted ecosystems. While these ideas are still under investigation, the fact that the boundary of the solar system is more active than previously thought adds weight to the possibility. The new data has led some scientists to propose that the solar system's journey through the galaxy is not just a passive drift, but an active experience, one in which our environment can be influenced by external cosmic conditions on a cyclical basis. In other words, we may be periodically exposed to more radiation depending on where we are in the galaxy, and those variations could have played a role in shaping the history of life on Earth. But what makes this especially compelling is that such events might leave traces. Some researchers are now looking into ice cores, sediment layers, and tree rings for clues about past changes in cosmic radiation. If consistent patterns emerge, it could support the idea that galactic conditions, not just solar activity or volcanic events, have helped drive major changes in Earth's climate and biosphere. But the implications go beyond Earth. If the outer boundary of the solar system is a dynamic, structured region that responds to galactic forces, then every planet within the sun's reach is affected in some way. That includes Mars, with its thin atmosphere and limited protection from radiation, as well as the gas giants, which may experience their own interactions with interstellar material. In practical terms, this means future space missions will need to consider the nature of the heliopause more seriously. If its properties can change over time, becoming more porous or turbulent, for example, then spacecraft and potential crewed missions outside the inner solar system may face radiation levels far different from what we'd expected. The design of spacecraft, shielding, navigation systems, and even long-term habitat planning might have to account for the changing conditions of this outer space frontier. Beyond the practical concerns, Voyager 2's findings have also sparked new philosophical questions. What does it actually mean to leave the solar system? If the boundary is not fixed or uniform, then crossing it may not be a single event, but part of a longer process, a transition from one kind of space to another. This has led some scientists and thinkers to describe the heliopause not as a wall, but as a membrane, something semi-permeable, reactive, and possibly even intelligent in the way it interacts with the surrounding galactic environment. This shift in thinking mirrors similar changes in how we understand Earth's atmosphere, or the interface between the ocean and the sky. In those systems, we've come to see boundaries as zones of exchange, where energy, matter, and information are constantly flowing. It now appears that the boundary between solar and interstellar space might behave in a similar way. One possibility being explored is that the region Voyager 2 is exploring could be a site of ongoing chemical activity. The unique conditions, low temperatures, high radiation, and the mixing of different kinds of plasma might allow reactions to occur that don't happen elsewhere. These could include the formation of complex organic molecules, the kind that are often considered precursors to life. If true, then the outer edge of the solar system might also be a zone of synthesis, where materials that eventually seed planets are born or transformed. This ties into broader questions about where and how life begins in the universe. For decades, scientists have searched for life on planets and moons, but there's growing interest in the idea that the building blocks of life might form in space itself, in the dust clouds between stars and comets, or possibly in transition zones like the one Voyager 2 is traveling through. These materials could then be delivered to young planets by collisions or drifting debris. In this view, the solar system is not an isolated system, but a participant in a much larger galactic process, exchanging materials, energies, and even biological ingredients with its surroundings. It's a radically different way of thinking about our place in the cosmos. We're not just observers, we're part of a network. And Voyager 2, by passing through this edge zone, is giving us the first direct evidence that this network exists and is far more active than we imagined. Another implication that researchers are starting to explore is how this knowledge might influence future exploration of nearby star systems. If each star has its own heliosphere and each boundary behaves differently depending on its location in the galaxy, then understanding our own boundary gives us a template for studying others. It may help us determine which stars have stable environments for planets, or how likely it is that planets within those systems could support life. In the long run, Voyager 2's journey could help us map the structure of the galaxy itself, not just its stars and planets, but its invisible skeleton of magnetic fields, plasma currents, and radiation zones. These are features that don't show up in traditional images, but are now being revealed through long-term observation and persistent data gathering. The more we learn about this edge region, the more it challenges the neat categories we've used for decades. We used to divide space into solar and interstellar, known and unknown, but now it's clear that there's no sharp line. The boundary is a space of transition, where identities blur and new possibilities emerge. Voyager 2's role in all of this cannot be overstated. It is not just collecting data, it is redefining categories, prompting new theories, and expanding our sense of scale. Its discoveries remind us that some of the most profound scientific progress doesn't come from shiny new tools, but from old instruments that endure long enough to stumble into something completely unexpected. One of the most unexpected developments has been the detection of what appear to be wave-particle interactions unlike anything previously observed in such distant space. Traditionally, this type of interaction has only been seen near highly energetic sources like stars or black holes. It involves particles riding along magnetic or electric field waves and gaining or losing energy in the process. Voyager 2, however, has detected a new kind of resonance. one that allows energy to move between particle groups without the usual signs of heating or turbulence. This finding suggests that energy can be transferred in ways that had not been considered before. It points to the possibility of unknown forces or structures organizing this transfer over vast distances. These guiding features may be magnetic filaments, electric field lines, or something even more exotic, possibly ancient remnants of galactic events like supernova explosions or long dissipated shock waves. Incredibly, this resonance has remained coherent across wide areas, meaning it doesn't break down as quickly as expected. That coherence implies the presence of something maintaining structure in an environment that was once assumed to be chaotic. The presence of such organized behavior in what should be empty space is one of the clearest indications yet that interstellar space is far more complex than any current models predict. In addition to this, Voyager 2 has recorded signs of temporal oscillations, shifts in the density of particles that appear to happen in regular cycles. These aren't directly tied to solar activity, and they don't line up with known galactic events either. This kind of pulsing behavior suggests that some unknown periodic influence may be acting on the region. Theories range from gravitational ripples caused by ancient stellar movements to wave-like patterns in the density of interstellar gas, to even more speculative ideas involving exotic forms of matter such as dark matter. Anyway, the point I'm trying to make is once again the density of our galaxy matters so much that even our idea of a big. Further complicating the picture is the observation of spatial anisotropy. Instead of a smooth gradient of changes moving outward from the Sun, Voyager 2 is detecting a twisted, uneven boundary zone. In some directions, the fields and particle flows are strong and active. In others, they appear weak and calm. This asymmetry doesn't match what would be expected based on the Sun's position in the galaxy or the general layout of the Milky Way. It suggests that unknown forces, perhaps distant magnetic sources or interstellar turbulence, are shaping the heliosphere in ways we don't yet understand. Then there's the matter of time. Not time in a science fiction sense, but in how events and interactions seem to unfold in this region. Some of the data suggest a form of temporal delay. Particles arrive with energy profiles that imply they should have interacted or degraded earlier in their journey. This has led to speculation that something in the structure of space itself could be altering the timing of energy exchange, almost like an echo or time lag caused by unusual field dynamics. It may be a result of how these particles travel along magnetic field lines or how they interact with the complex plasma in this region. Adding yet another layer of mystery, Voyager 2 has picked up low-frequency electromagnetic tones in the plasma. These are extremely deep humming vibrations that, when converted into sound waves, form patterns similar to standing waves. On Earth, standing waves are found in musical instruments or confined fluid systems. In deep space, their presence suggests that something is containing or reflecting energy over very large distances. These tones may help explain how energy and information move through the interstellar medium, and they may even offer insight into how space structures itself on massive scales. There's also speculation that these plasma vibrations could one day be used for space travel. If these waves can carry energy over long distances without losing strength, future spacecraft might be able to harness them, riding them like waves on the ocean. Though this idea is still theoretical, the fact that such coherent patterns exist at all challenges our assumptions about space as a random or inert environment. Voyager 2 has also reported rapid changes in temperature across very small regions. These aren't gentle shifts, they're sudden spikes or drops, sometimes occurring over just a few kilometers. It's a bit like encountering a weather front in space. These temperature variations could indicate tiny boundaries or shock fronts, each with its own characteristics. It means that space weather in the outer solar system may be far more varied and dynamic than previously assumed. For future space missions, understanding these small-scale fluctuations could be vital for navigation and long-term planning. All of these observations raise new questions about what the edge of the solar system really is. For a long time, scientists treated it as a clear line, the end of one domain and the beginning of another. But Voyager 2's findings suggest it may be more like a transition zone or a threshold where properties mix, overlap, and change in unpredictable ways. This also affects how we define the solar system itself. If the heliopause is reactive and variable, then it's not really a wall, but a kind of breathing membrane that moves, adapts, and responds to galactic conditions. The solar system might not be a closed bubble, but a semi-open system, constantly interacting with the galaxy around it. To model this complexity, researchers are now having to rewrite parts of physics. The traditional tools used to understand plasma, magnetic fields, and particle motion are proving inadequate. New equations and simulations are being developed that account for feedback loops, chaotic patterns, and even quantum-level interactions. These models could help us understand not just the space around our own star, but the environments surrounding others. There's also the possibility that some of these conditions help facilitate chemical reactions that wouldn't happen anywhere else. Traces of heavy elements and unusual molecules have already been detected in the region Voyager 2 is passing through. These may be the remains of distant stellar explosions gradually drifting through the galaxy. If the right kinds of radiation and materials are present, these regions might support the formation of organic compounds, potential ingredients for life. Out of this view, the boundary of the solar system is more than just a protective shell. It might be a place where raw cosmic materials are processed, altered, and potentially turned into building blocks for future worlds. Some scientists now believe that similar boundary zones around other stars could play a role in creating the ingredients necessary for life across the galaxy. Voyager 2 is also teaching us about what happens to spacecraft themselves when exposed to such conditions for long periods. The probe has become a kind of test subject for material science in space. Its slow degradation, power output, and responses to radiation offer valuable information about how long missions could survive in deep space environments. Perhaps most intriguing of all are the faint unusual signals Voyager 2 continues to detect, repeating radio patterns, unexplained deflections of high-energy particles, and behavior that hints at unknown physics. Some of these may one day lead to the discovery of new forces or particles, or even indirect evidence of phenomena like dark matter. While none of the findings point directly to anything artificial or engineered, the fact that they are so far outside current models has forced scientists to keep an open mind. Voyager 2's journey is not just about distance or endurance. It's about discovery of structures, patterns, and behaviors in space that no one predicted. Its continued movement through this complex region offers a rare, real-time look at how our solar system fits into the broader galactic context. Every signal it sends home carries with it the potential to rewrite a small part of what we know about the universe. And so, as this aging spacecraft drifts further from the sun, it carries with it the curiosity of the species that built it. Still transmitting, still discovering, Voyager 2 is not just exploring the edge of our solar system, it is pushing against the edge of human understanding.